In 1910, two of the greatest minds in logic set out to prove something every child knows. It took them nearly 300 pages just to establish that 1 plus 1 equals 2. To a non-mathematician, spending hundreds of pages on 1 plus 1 sounds like the ultimate academic joke. But behind this monumental effort was a deep crisis that threatened to destroy all of mathematics. The work was called Principia Mathematica, a 3-volume monster written by Bertrand Russell and Alfred North Whitehead. Its goal was simple yet terrifying: rebuild mathematics from scratch. Why did math need to be rebuilt? Because in the late 19th century, mathematicians realized that their foundational assumptions were built on quicksand. Welcome to Act 1, the crisis in logic. To understand why 1 plus 1 is so hard to prove, we first have to examine how naive set theory exploded. In the late 1800s, German mathematician Georg Cantor introduced set theory. He defined a set simply as any collection of distinct objects. Another pioneer, Gottlob Frege, attempted to use Cantor's set theory to ground all of arithmetic. He believed that numbers were nothing more than sets of sets. In Frege's view, the number 0 is the set of all empty sets. The number 1 is the set of all sets containing exactly one element. Similarly, the number 2 is the set of all pairs. It seemed elegant, simple, and completely rigorous. Math was finally on firm logical ground. Then in 1902, Bertrand Russell sent a short letter to Frege that shattered the entire system overnight. Russell asked a simple question: consider the set of all sets that do not contain themselves. Does this set contain itself? If it does contain itself, then by definition it shouldn't. But if it doesn't contain itself, then by definition it must. It was a fatal contradiction. This paradox proved that naive set theory was flawed. If logic itself could produce contradictions, then every mathematical proof ever written was potentially invalid. Frege was devastated. Upon receiving Russell's letter, he added an appendix to his book stating, "Hard to imagine a more unfortunate thing than to have the foundation give way just as work is finished." Russell realized that to save mathematics, he couldn't just patch up set theory. He had to build an entirely new, bulletproof foundation from scratch. Act 2, Building Principia. Russell partnered with his former teacher, Alfred North Whitehead, to construct a system where paradoxes were physically impossible to express. To eliminate Russell's paradox, they developed the theory of types. In this framework, objects are organized into a strict hierarchy of levels. Level 0 consists of individual objects. Level 1 consists of sets of objects. Level 2 consists of sets, and so on. A set can only contain elements from lower levels. Because a set at level n can only contain elements from level n-1, a set can never contain itself. Russell's paradox was banished by definition. With paradoxes ruled out, Russell and Whitehead began constructing mathematics from absolute zero, accepting no intuitive assumptions. They started with basic primitive symbols: implication, negation, disjunction, and existential quantifiers. Every single deduction had to be rigorously proved step by step. Before they could even talk about numbers like 1 or 2, they had to establish basic rules of logic, such as if P implies Q and P is true, then Q is true. It took over 50 pages just to establish the formal mechanics of logical variables and connective operators before set theory could even begin. The project demanded immense precision. Every definition built atop earlier definitions without skipping a single intermediate logical link. By Volume 1, page 100, Russell and Whitehead reached the definition of classes and relations, preparing the ground for cardinal numbers. Notice how alien this logic appears. To say that a set contains one item, you can't just count it. You must express it purely in terms of existential quantifiers. Act 3, the 300-page proof. Let's look closely at how Principia Mathematica finally defines the number 1, the number 2, and addition. First, how do you define the number 0? 0 is defined as the cardinal number of the empty class, written as the set containing only the empty set. Next, what is the number 1? In Proposition 54.43, Russell defines 1 as the class of all unit sets, sets that contain exactly one element. Translating that symbol into plain English, 1 is the collection of all sets alpha such that there exists some element x where alpha contains only x. Now, what is the number 2? Russell defines 2 as the set of all couples, sets containing two distinct elements x and y. We have 0, 1, and 2 defined as formal classes. Now comes the crucial step, defining arithmetical addition. Addition of cardinal numbers is defined via disjoint union. If set A has cardinal alpha and set B has cardinal beta, and A and B share no elements, their union has cardinal alpha plus beta. To prove 1 plus 1 equals 2, you must pick two disjoint unit sets, combine them, and prove that the resulting set satisfies the formal definition of 2. This sounds straightforward, but under the strict rules of type theory, you must first prove that two disjoint unit sets actually exist in the logical universe. If the universe contained only one single object, you could never form two disjoint unit sets, meaning the number 2 would be an empty class. Finally, on page 362 of Volume 1, Russell and Whitehead state proposition star 54.43. Here is the exact formula as printed. Star 54.43 proves that if alpha and beta are unit classes and disjoint, their cardinal sum is 2. Right below this formula, Russell dryly added a famous footnote. From this proposition it follows that, when 1 plus 1 is defined, 1 plus 1 equals 2. Notice the subtle phrase, when arithmetical addition has been defined, because full cardinal addition was not formally completed until Volume 2, page 86. Act 4, Gödel's bombshell. Russell and Whitehead thought they had saved mathematics. But 20 years later, a 25-year-old Austrian mathematician destroyed their entire dream. In 1931, Kurt Gödel published his incompleteness theorems. He proved that no formal axiomatic system can ever be both complete and consistent. Gödel showed that you must choose between consistency and completeness. If your system is consistent, there will always be true statements that cannot be proven inside the system. Gödel achieved this by inventing Gödel numbering, assigning a unique integer to every logical symbol, formula, and proof in Principia Mathematica. Using these numbers, Gödel constructed a self-referential statement G that effectively says, this statement cannot be proven within Principia Mathematica. If statement G is provable, then Principia is proving a false statement, meaning it is inconsistent. But if G is unprovable, then G is true, meaning Principia is incomplete. In one brilliant stroke, Gödel proved that Russell's grand dream of encapsulating all of mathematics into a single complete logical framework was mathematically impossible. Russell later confessed that Principia Mathematica exhausted his brain power so completely that he never fully recovered his mathematical abilities. Despite Gödel's proof, Principia was not a failure. It fundamentally transformed computer science, mathematical logic, and automated theorem proving. Today, every modern static type system in programming languages like TypeScript or Rust owes its conceptual parentage directly to Russell's theory of types. Act 5, The Modern View. How do mathematicians define 1 plus 1 equals 2 today, without spending 300 pages? Today, arithmetic is built on the Peano axioms, formulated by Giuseppe Peano in 1889. Peano defines natural numbers using a successor function s. In Peano arithmetic, 0 is a natural number. 1 is defined as the successor of 0, s of 0. 2 is defined as the successor of 1, s of 0. Addition in Peano arithmetic is defined recursively by two simple rules, a plus 0 equals a, and a plus successor of b equals successor of a plus b. Now watch how fast we can prove 1 plus 1 equals 2 in Peano arithmetic. We start with 1 plus 1, which is 1 plus successor of 0. Using Rule 2, 1 plus successor of 0 equals successor of 1 plus 0. Using Rule 1, 1 plus 0 is simply 1. So successor of 1 plus 0 becomes successor of 1. And by definition, successor of 1 is 2. The entire proof takes just 4 lines instead of 300 pages. Why did Peano take 4 lines while Russell took 300 pages? Because Peano assumed natural numbers exist as primitives, whereas Russell tried to derive numbers themselves from logic. In modern mathematics, the standard foundation is Zermelo-Fraenkel set theory with choice, known as ZFC. In ZFC, numbers are defined using von Neumann ordinals. 0 is the empty set, 1 is the set containing 0, 2 is the set containing 0 and 1. Every number in von Neumann's system is literally constructed out of empty sets. Numbers are just nested Russian dolls of pure emptiness. Today, software like Lean, Coq, and Isabelle allow computers to verify mathematical proofs automatically with absolute certainty. In the Lean Proof Assistant, proving 1 + 1 = 2 takes just a single line. Theorem 1 + 1 = 2 by RFL, meaning true by definition. Behind that single word RFL lies decades of formal logic work pioneered by Russell, Whitehead, Peano, and Gödel. Let's synthesize what we've learned. Why does a 300-page proof for 1 + 1 matter to us today? First, it showed us that intuition is dangerous in mathematics. What seems obvious can easily conceal deep logical contradictions. Second, it birthed the concept of formal syntax and mechanical computation long before physical electronic computers existed. Alan Turing was heavily inspired by Principia Mathematica and Gödel's work when he invented the Universal Turing Machine in 1936. Without Russell's obsession with 1 + 1, modern computer software and artificial intelligence reasoning engines might not exist. As we build artificial general intelligence, AI agents are returning to formal proof assistants like Lean to guarantee zero hallucination in mathematical reasoning. So the next time someone tells you that 1 + 1 = 2 is obvious, remember Bertrand Russell and the 300 pages it took to prove it. It stands as a testament to humanity's relentless quest for absolute certainty in an uncertain world. Thank you for watching this deep dive into the foundations of mathematical logic. If you enjoyed this video, hit the subscribe button, leave a comment, and let us know what mathematical mystery we should explore next. Until next time, keep questioning the foundations of what seems obvious.